All right, so recall that we're talking about conditional expectation, and we are doing this rather long proposition which listed many, many properties of conditional expectation. Last time we got to property number 9, so I want to add maybe one or two properties more, and then I want to, switch gears a little bit. So unfortunately, perhaps the rest of the next few lectures may seem like we're doing a little bit, bits and pieces of various things. But I think in the interest of, given the amount of time we have, I think that may be something we have to do. Anyway, so let me go ahead and turn off the camera and share the iPad screen with you. Oh, wait, I have to, before I do that, I need to start this. Since iPad. All right, so now I think I can do this, share a window. All right, so the iPad screen is visible, I hope. All right, so here's where we are. Now we're doing various properties of conditional expectation. And the property we did last time was the following. So we said, suppose you have x and z, which are both integrable random variables. Okay, and I want to take e of zx given g. Right now, suppose z is g measurable, then basically you can pull it out. That's basically what you're saying. So in other words, since if z is g measurable, you can just pull it out here, as has been done on the right side. To justify this operation, we need a little bit of integrability. And there are a couple of different ways you can get integrability. One is if z is bounded. Another is if x is an LP, z is an LQ, and so on. So this is something we had done last time, right? This basically said that when something is already measurable with respect to the sigma algebra, you can just pull it out. The last property, perhaps, of conditional expectation I want to state is what happens if you take conditional expectation of a random variable which is independent of the sigma algebra. Okay, this is good. Okay, so is there any room for number 10 here? Okay, so can I just sneak in number 10 here? So that's what I'm going to do. Number 10. So please make a note, okay? I've come back to this site on proposition and I'm adding some stuff here. So proposition number 10 is if x is independent of g, then, so before I write out what the answer is, let's think for a second. That we're talking of e of x given g. Right? What are we thinking of this object as? We're thinking of this as the best guess of x given all the information in g. Now, if you are told that x is independent of g, that means that knowing g tells you nothing about x. And now I ask you, given that you have information g, which tells you nothing about x, what is your best guess of x? Your answer would be, well, my best guess of x is simply the expectation of x. So the following is hopefully intuitively believable and all that. Of course, we have to prove this, but I hope the intuition behind this is clear to you. No, okay. So suppose x is independent of g, and you're trying to get the best guess of x given g. Well, g doesn't give you any information about x, so the best guess of x is just going to be the expectation of x. Of course, you have to have p almost surely here, because remember that even though this is a number, this left side is a random variable. And so this random variable is constant almost surely. Okay, so this is what I want to prove. So actually, let me just go back here and let me mention that this is proof of number 9. And now let's prove number 10. Okay, so let me just rewrite this. So suppose x is independent Independent, not depend, independent of G. What do we want to do? We want to show that E of x given G equals E of x P almost surely. Okay, so now we remind ourselves of the definition of conditional expectation. We want to show that the right side is the conditional expectation of x given G. Well, if we want to do this, we need to do two things. One is we need to convince ourselves that the right side is G measurable. Now that I claim is automatic. Why is that automatic? Well, the right side is a constant, right? A constant function is definitely G measurable. I'll leave it to you to think about that. And clearly, E of x being a constant is G measurable. Okay, so completely shamelessly, even though I said clearly this is true, I will still ask you to just ask yourself, just justify why. Why is it that a constant function must be G measurable? Okay, so clearly Ex being a constant is G measurable. So what do we need to do? So let G in G. So we need to show that what do we need to show? We need to show that expectation indicator G times the random variable equals the expectation indicator G times whatever we think its conditional expectation is. So this is just from the definition of conditional expectation. This is what we need to show. Let me write this down in terms of integrals, i.e. we need to show the integral over G of x dp equals the integral over G Ex dp. Now note that on the right side, the integrand you're looking at, Ex is a constant. So you know that the integral of a constant with respect to a measure over a set is just going to be the constant times the measure of that set. So this is just going to be E of x times P of G. This is what we want to show. Great. So let's see why this is true. Okay, so let's look at the integral over G x dp. Right, so what is this? This is the integral over omega indicated G x dp, right? So what is this? This is expectation indicated G times x, right? And now I'll use the following facts. Remember, G has been taken from this sigma algebra, and this sigma algebra and x are independent. So I claim that this function indicator G and x are going to be independent. So this is going to be E of indicator G times E of x. Let's make a comment. So since G is in the sigma algebra G, and x is independent of G, the random variables indicator G and x are independent. And you know that independent means multiply. And so that's what we're doing here. And so of course now what I'll get is I'll basically get P of G times E of x, which is exactly what I wanted to show, and so I'm done. Okay, any questions so far? Questions? Okay, so the one thing that we have not said anything about is conditional probability. And that may be something that may be coming to your mind, because when you studied probability as an undergraduate, if you studied it, you would have probably first learned conditional probability, then learned conditional expectation. Here we have not said anything about conditional probability. So what is conditional probability? The answer is, in the measure theory case, you first define conditional expectation, and then you define conditional probability in terms of that. Okay, so what about conditional probability? The answer to the question is we're going to define this concept in terms of conditional expectations. So before I do that, let me just make a quick note. Suppose I have a probability space omega fp, okay, and I take A, which is an F. Note that P of A is just E of indicator A. Okay, so the probability of a set is the expectation of the indicator random variable of that set. So what have I done here? I have taken a measurable set and I've associated to it a random variable. And probability of the set is just the expectation of the indicator function of that set. So this kind of gives us some hint as to how we may go about defining conditional expectations, conditional probabilities. So we will say, by the way, this is about ordinary probabilities. Okay, so this is old news. This is something you have known for months. Okay, this is nothing new here. But what this suggests is that maybe you can define conditional probability just as probability of a set is the expectation of the indicator function of the set. Maybe you should define conditional probability to be the conditional expectation of the indicator function of that set. And that is exactly what you do. Okay, so here is how you get conditional probability. So let omega fp be a probability space. And let G, a subset of F, be a sigma algebra. All right. So for any A in F, we define the conditional probability of A given G, right? We'll denote this by P of A given G to be E of indicator A given G. Now remember that this quantity you know how to make sense of, right? Because indicator A is a random variable. It is actually an integrable random variable. And so you can talk about this quantity that I'm now circling. So whatever this quantity is, take that as your definition of P of A given G. So i.e., define P of A given G to be E of, and here this is a definition, okay? So if you're asking why are these two equal, I'm saying they're equal by definition. By definition, I'm saying that the thing on the left side is defined to be the quantity on the right side. E of indicator A given G. All right. So anyway, so this is how you get conditional probabilities. Right? So you first do conditional expectations and then define conditional probabilities in terms of that. All right, so now, as I said, we will be jumping around a little bit, doing a few different things. Any questions before I go on? All right, so here's what I want to do. I want to see if we can spend some time talking about limit theorems. Okay, so this is a very important topic. I mean, there are several important topics we can talk about. One is limit theorems, like law of large numbers, central limit theorem. Another thing that we are well prepared to do is also to look at some stochastic processes, in particular, to look at a class of processes called martingales, which have a lot of importance. They're quite intimately connected with gambling. And it turns out that there are a lot of things you can prove in probability by using martingales. So those are kind of the two topics that are on my mind. So limit theorems on the one hand, and martingales on the other. So let's see what we can accomplish. But what I want to do is I want to first. So there is. I mean, I'm thinking in terms of low-hanging fruit. Okay, so there is a simple law of large numbers that we can prove without much difficulty. So I feel that let's do that first. Okay, so in order to do that, what I'm going to do is I'm going to, let me just do a search here. All right, here we go, page 148. All right, okay. This was LP spaces, blah, blah, blah. Limit theorems. Okay. Okay, this was just before conditional expectations. All right. So we have scribbled this before, so I want to minimize the amount of writing. Okay, so we said limit theorems play a central role in probability. Limit theorems is basically asymptotic theorems. Okay, we said there are several types of limit theorems. There's law of large numbers, the central limit theorem. Once again, there's no unique law of large numbers. The law of large numbers is like ice cream. There are many flavors of ice cream, but they're all ice cream, right? And maybe central limit theorem is like chocolate, and there are many different types of chocolate, but they're all chocolate. So when I say I have a law of, I won't say the law of large numbers. I will say, or I may, for a specific context, I may say the law of large numbers for this family of random variables. But in general, for different families of random variables, you'll have different laws of large numbers. Anyway, so here is a little bit about certain laws of large numbers. So suppose I have omega fp, which is a probability space. And suppose I have x1, x2, and so on, which is a sequence of independent, identically distributed, real-valued random variables on omega. Okay, so you know what independent means? It means that the x1 does not give you any information about x2, no xi gives you any information about xj. And identically distributed, meaning they have the same CDF, or if you prefer, they have the same law. Suppose further that expectation of xi is 0, and the variance of xi is sigma squared in 0 infinity. Let Sn be the sum I going from 1 through n xi. Okay, so now if you want an example, what you can think of is the following. You're going to toss a coin infinitely often. Okay, if you get a head, you will say that the random variable x for that toss is 1. If you get tails, you will say that the random variable for that toss is 0. Put another way, the first time you toss, if you get head, then x1 is 1. If you get tail, then x1 is 0. The second time you toss, if you get head, then x2 is 1. If you get tail, x2 is 0, dot, dot, dot. And I'll take Sn to be the sum I going from 1 through n xi. So in this coin tossing example, this is the total number of head you get in n coin tosses. Now, okay, I can't do this. I'm sorry, interestingly, I made the same mistake the previous time I did this. We want ex1 to be 0. All right, so my bad. Let me do the following. I'll toss a coin. If I get heads, I'll take x to be 1. If I get tails, I'll take x to be minus 1. Okay, and I'll be tossing a fair coin. I need both those things. So I'll toss a fair coin the first time. If I get heads, I will say that x1 is 1. If I get tails, I will say x1 is minus 1. Now, then I'll toss the coin a second time. If I get heads, I'll say x2 is 1. If I get tails, I'll say x2 is minus 1. Now, this is a fair coin, so you're equally likely to get heads as you are to get tails. So you can easily check that expectation of x1 is 0. Now I will look at Sn, which is the sum I going from 1 through n xi. Now what is this? This is the total number of heads that you get, right? All right, now your intuition tells you that roughly heads and tails should come up 50-50. So if I look at 1 over n Sn, that should approach to 0 as n goes to infinity, and that is in fact true. And if I make a statement that 1 over Sn goes to 0 p almost surely, so first of all, if I say 1 over n Sn goes to 0, this is a law of large numbers. The fact that the convergence is happening almost surely makes it a strong law of large numbers. Okay, so for L2 random variables, we have already seen a weak law of large numbers. Okay, so this we had done. If I say 1 over n Sn goes to 0, that's a law of large numbers. If this goes to 0 in probability or in L2, then it's a weak law of large numbers. Now for L2 random variables, I believe we have done a weak law of large numbers. I don't know where it is in all these. The number of pages is right now at 174. Unfortunately, I don't know where it is. But I will just say that for L2 random variables, we have done a weak law of large numbers. Actually, there we go. It's right here. Weak law of large numbers for L2 random variables. Okay, so suppose xi, I going from 1 to infinity, is a sequence of independent, identically distributed L2 random variables on omega fp with expectation xi is 0 and variance of xi is sigma squared less than infinity. Let Sn be the sum I going from 1 through n xi. Then 1 over n Sn converges to 0 in L2. So this is something we did. This was a pretty easy calculation. Now remember, if you showed that this convergence happens in L2, then you remind yourself that convergence in LP implies convergence in probability. So actually 1 over n Sn converges to 0 in probability. So that's why it's called a weak law of large numbers. Now it turns out that for this thing, you can also prove a strong law of large numbers. And all you need actually is that you don't even need the random variables to be L2. But you have seen in math, the more assumptions you put, the easier it is to prove something. The less assumptions you put, the harder it is to prove something. Now, since this is the first time you're learning this, I think it's not a bad idea to put a little more assumptions and quickly see a proof of the result. That's not a bad idea. That has some value. So that's what I'm going to do next. I want to, so weak law of large numbers for L2 random variables is done. Okay, now it turns out weak law of large numbers for L1 also is true. No problem there. But what I want to do is I want to do a strong law of large numbers. I want to show that 1 over n Sn goes to 0, p almost surely. Now, these assumptions are enough to guarantee it. But to prove it using these assumptions will require quite a bit of work. But it turns out, if I just assume that instead of L2, everything is in L4, then there is a very easy proof of the strong law of large numbers. So I think that is a worthwhile exercise. So what I want to do is I want to prove a strong law of large numbers. All you need is that the random variables are L1. However, if you assume that they're L2, your proof becomes easier. If you assume that the random variables are in L4, then actually the proof becomes really easy. And I think that's a cool derivation, so I want to do that. So that's where I want to go next. Okay, so I want to prove an easy, strong law of large numbers with perhaps a significant assumption that the random variables are in L4. Okay. So by the way, this is taken from the book by David Williams. And maybe let me just turn the camera on and just kind of flash it on the screen in front of you. There's the book by Williams. It's a really nice book. Okay, so here he has this chapter which he calls chapter 7. He calls an easy strong law, and you'll see why it's an easy strong law. Okay, so the next thing I want to do is I want to prove a strong. By the way, can you see the iPad?
Yes, sir.
Okay, so I want to prove a strong law of large numbers. Right, often you will see this abbreviated as SLLN for obvious reasons. Okay, so what is the strong law of large numbers going to say? So suppose that x1, x2, dot, dot, dot are independent random variables, and that for some constant k, in 0 infinity, in other words, for some non-negative constant k, we have expectation of xk equals 0 and expectation of xk to the power 4 is less than or equal. This is not so good, right? Because I'm using k as an index and also as a, let me change this a little bit. Let me say xn, okay? Because I don't want people to get confused with which k is small and which k is uppercase. Okay, we have e of xn is 0. Okay, maybe xn isn't the greatest idea. Let's go with xj. xj to the 4 less than or equal to k. For all j greater than or equal to 1. Okay, so what are we saying? We're saying suppose that x1, x2, dot, dot, dot are independent random variables. And suppose that for each j, e of xj is 0. So each xj is 0 mean. And further, the fourth moment of each xj exists. So e of xj to the 4 is finite. Moreover, you can, if you look at e of xj to the 4, for all j that can be bounded above by one single constant k. So you can find one single constant k such that for all j, expectation xj to the 4 is no more than k. By the way, do you notice anything a little different about this thing in the first sentence? Do you see something different, something missing, something added? So just 5 minutes back, we were looking at another slide which had laws of large numbers. Do you see any difference? Mukesh? Saraswati? Nandini? Somnath?
I think, sir, we're taking sigma to be the same for each random variable.
Yes. Refine that.
What, sir?
Okay, so basically what you're saying is that earlier we assumed identically distributed, and here identically distributed is missing. That's, I think, what you want to say. So note that this particular law of large numbers does not require identically distributed. If you put in identically distributed, nothing is going to happen. Nothing bad is going to happen. But I just want to note that this particular proof does not require x1, x2, and so on to be identically distributed. Remember, if they're identically distributed, then their expectation is going to be the same, the second moment is going to be the same, the variance is going to be the same, everything. So if they were identically distributed, then this number would be independent of j. Okay? If the random variables were identically distributed, then this number here would be independent of j. But here we're allowing that they're not identically distributed. That's why we're making this fuss and saying that there should be a single number k such that for all j, e of xj to the 4 is less than or equal to k. All right, now, by the way, here what I'm saying is, I'm saying that the fourth moment of x exists. And way back earlier in the course, you did a problem where you showed that if the nth moment exists, then the n minus first moment exists, and the n minus second moment exists, and so on. So you prove that if expectation x to the 5 is finite, then expectation x to the 4, expectation x cubed, expectation x squared, all of those guys are finite. So as soon as I say that expectation xj to the 4 is finite, it follows that expectation xj cubed, xj, all of them are finite. Anyway, E of xj has to be 0 for all of them. Okay, so now here's a strong law of large numbers. So let Sn be the sum I going from 1 through n xi, like the usual thing. Then if I look at the probability of the set where 1 over n Sn converges to 0, that is 1. Another way to say that is 1 over n Sn converges to 0, P almost surely. All right, now why should it go to 0? Remember what you saw in these laws of large numbers is it should go to the mean. In this case, the mean of each of the random variables is taken to be 0. It's a strong law of large numbers because this convergence is going to happen P almost surely. Any questions with this? With the statement? Of course, I don't expect you to know what the proof is. That's something we want to do, but any questions with the statement? All right, so let's see how you prove this. Right, so let me start by looking at Sn to the 4. Okay, so this is going to be x1 plus x2 plus dot 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 up to xn to the power 4. All right, so now what I'm going to do is, let me just write out what you're going to get, or at least let me write out part of what you're going to get. Now you have done this sort of exercise. This is a painful thing to sit down and figure out what this is going to be, but it can be done. You have to sit with a lot of paper and pen and a strong cup of coffee, and you can figure out what it's going to be. But you know what's going to happen. You'll have x1 plus x2 dot 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 up to xn, another bracket, you know what you'll get. So basically, I think you will all agree with me that I'm going to get x1 to the 4 plus x2 to the 4 plus dot 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 up to xn to the 4. I think everybody agrees with that, yes? Those are not the only terms, but those will definitely be there. So we'll definitely get sum I going from 1 through n xi to the 4. This will definitely be there. But again, there will be other terms also. Then I think you agree with me that you will get terms of the type x1 squared, x2 squared, and you'll get terms of the type x3 squared, x5 squared. Now I'll leave it to you to check that this is what you'll get. You'll get 6 times the double sum I less than j. Okay, so if I'm doing that, then maybe what I should do, well, actually, let me just write one sum. This is a sum over ij such that I less than j. So let me just write here. This is actually the summing over 2 indices. Okay. This I'll leave it to you to check. You'll get 6 times sum over all ij such that I is less than j. Now remember, if I is less than j, then I and j cannot be the same. Xi squared, xj squared, plus other terms. Okay, and what are the other terms going to be? Will be of one of following 4 types. So let I, j, k, l be distinct indices. So what are the 4 types of terms we'll get? One is we'll get things of the form xi cubed xj. Another thing we'll get will be of the form xi, xj, xk squared. And the remaining type of thing we'll get is xi, xj, xk, xl. Any questions so far? Let me just recap what I've done. I'm looking at, so Sn is the sum of xi I going from 1 to n. Now I'm taking Sn to the 4. So I'm taking x1 plus x2 plus dot 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 up to xn, the whole thing to the power 4. Now you can expand this out. It is going to be one unholy mess, but you have some idea what's going to happen. All the terms will be products of 4 x's. No less, no more. All the 4 x's may have the same index, so it may be something like xi to the 4. You may have xi squared, xj squared, where I and j are different. You may have xi cubed, xj, where I and j are different. You may have xi, xj, xk squared, where I, j, k are different. And you may have xi, xj, xk, xl, where I, j, k, l are different. Any questions with this? There are no other terms that will show up. Any questions with that claim? So the claim is when I expand this out, I will get this term, sum I going from 1 through n xi to the 4, plus 6 double sum I less than j xi squared xj squared. Here I is less than j, so I and j are different, plus other terms. And these other terms, I think my counting is kind of poor. I said the other terms can be one of following 4 types, but I have only written 3 types. And unfortunately, nobody has said anything. So let's fix that. Okay, so there will be, the other terms will be of precisely one of 3 types. So far, so good? All right, I'll take that as a yes. Now what I'm going to do is I'm going to take expectation of Sn to the 4. Okay. Now the reason I did not write out what these other terms are is because when I take expectations, I'm going to get 0. So let's look at expectation of other terms. Right, so suppose I look at a term of the type xi cubed xj. Remember, let me actually go ahead and decorate this a little bit. This is being used throughout, okay? I, j, k, l are distinct indices. Maybe that's not enough decoration. Maybe we need some more decoration. So let's do the following. Okay, so when you're seeing I, j, k, and l, they are distinct indices. Okay, so if I take e of xi cubed xj, remember, I have independence. So this is e of xi cubed, e of xj. You have learned this. If I take a product of independent random variables and I take the expectation of the product is product of the expectations. But wait a second. What is e of xj? Well, this is just 0 because all the random variables have been assumed to have 0 mean. Okay, that means if you look at this first type of other term, when I take its expectation, I'll get 0. Now let's look at the second other term. So now if I look at e of xi, xj, xk squared. Now again, I will use independence and I will get this as e of xi, e of xj, e of xk squared. And once again, this is going to be 0. So this term is also going to be 0. Similarly, e of xi, xj, xk, xl, I don't have the patience to write it out. This is going to be 0. Again, you're going to use independence. Okay. All right, so basically using independence. Okay, so let me say this. Because of independence, and E of xj equals 0 for all j, and we have E of other terms equals 0. Any questions with this? Questions? Okay, so now what am I going to get? So now, if I take expectation of Sn to the 4, this is going to be the sum I going from 1 through n, E of xi to the 4 plus 6 times, this is a double sum over I less than j. So I'm summing over all ij such that I less than j, E of xi squared xj squared. Any questions so far? Okay, so all I did is I just took expectations in this equation and I noted that expectation of other terms is 0. Okay, so now what am I going to do? So now I'll say, so now I'll use a fact here. I want to prove this fact also, but right now I'm just going to state it. Let me just state it in words here. Well, actually, so I have omega fp, which is a probability space, right? Okay, so suppose x is in LR of omega fp for each r greater than or equal to 1. Let's actually leave out the infinity case. Don't want to worry about that. So for all r in 1 infinity. Okay, so suppose x is in LR for omega fp, x is in LR omega fp for each r in 1 infinity. If p greater than q, and of course both of them should be greater than or equal to 1, then the q norm of x is going to be less than or equal to the p norm of x. This can be concisely summarized by saying the property you have is monotonicity of LP norms. Okay, so basically we're saying suppose a random variable x belongs to LP and it belongs to LQ. Okay. By the way, here I'm assuming that it belongs to LR for each R. That is not necessary. All I'm saying is if a random variable x belongs to LP and it belongs to LQ, and if P is bigger than Q, then the LP norm is greater than or equal to the LQ norm. We'll come back and prove this, but right now we'll just use this fact. Okay, any questions with what this is saying? If you don't know how to prove this, that's a different story, but any questions with what this is saying? All right, so let's come back here and see how LP norms come into the picture, and we'll be using this fact also. Okay, so what are you going to get? So now note that E of xi to the 4, this is going to be less than or equal to capital K. This we had on the previous slide. We knew that for any j, E of xj to the 4 is less than or equal to k. So this is true. Now, what are we going to do? How are the LP norms going to come into place? So here's how. Also, when I look at E of, okay, I should also mention ij have to be distinct. So for I not equal to j, when I look at E of xi squared xj squared, by independence, this is going to be E of xi squared, E of xj squared, right? But what is this? This is simply the L2 norm of xi squared times the L2 norm of xj squared. Any questions with that? Questions? All right, now what is this here? This guy is, I'm taking xi, I'm taking its L4 norm to the 4th power. And this is less than or equal to k. So what this is saying is that the L4 norm of xi is less than or equal to k to the power 1/4. All right, now why am I going to use that? So now let me come over here. So by monotonicity, monotonicity of LP norms, if I look at the L2 norm of xi, this is going to be less than or equal to the L4 norm of xi, which is less than or equal to k to the 1/4. So if I look at the L2 norm of xi squared, that is going to be less than or equal to root k. Similarly, if I look at the L2 norm of xj squared, that is going to be less than or equal to root k. So what am I saying? I'm saying that this guy is going to be less than or equal to square root of k. This guy is going to be less than or equal to square root of k. Any questions with this? Questions? So thus E of xi squared xj squared is less than or equal to k. So far so good. Now we will plug everything into this equation. So let me do the following. Let me copy this equation. Okay, so now what do we know? We know that this guy is less than or equal to capital K. And we know that this guy is less than or equal to capital K. Right? That's what we've shown on the previous page. All right, so now let's find out what the right side is going to be. So now let me, so we're going to get, so E of Sn to the 4 is going to be, not equal to, is going to be less than or equal to k times summation I going from 1 through n of just the number 1 plus 6k times double sum over I less than j of just the number 1. Okay, so what I've done is I've said that this guy is less than or equal to k. Let me pull the k out. And then the summation is still there, so I'm just going to be adding up 1 n times. Similarly here, the 6 is there. Then this is no more than k. I'll pull the k out. And then I have the sum, double sum of 1. Now, I'll leave it to you to check. So what's going on here? What is this? Now, of course, and let's see what this is. So this is going to be nk plus 6k n minus 1 over 2. Okay, now why is this true? So when I'm looking at, so the question is, how many terms are you adding here? Okay, so suppose, what is this? Okay, so if j equals 1, then nothing, right? I less than j is not possible. If j is 2, then I equals 1. If j is 3, then I equals 1, 2, dot, dot, dot. If j equals n, then I equals 1, 2, dot, 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 up to n minus 1. Any questions with this? So how many terms am I adding? 0 plus 1 plus 2, dot, 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 up to n minus 1. So now I will ask myself, what is the sum of j? What is the sum of the first n minus 1 integers? Sum j going from 1 to n minus 1. So you know this is going to be n minus 1 n over 2. That's how we got this quantity. Any questions with that? Questions? All right. So E of Sn to the 4 is going to be less than or equal to nk plus 3 n minus 1 k. All right. Now what I can do is the following. So I claim that this is less than or equal to, so this is nk plus 3 n squared k minus 3 nk, right? So what is this? This is 3 n squared k minus 2 nk. Now remember, if I'm subtracting something from 3n squared k, the result will be smaller than 3n squared k alone. So this is less than or equal to 3n squared k. Okay, so now what I'll do is I'll take expectation of Sn over n to the power 4. Right, so this is going to be less than or equal to 3k over n squared. Do you guys agree with this? Yes? Okay, so now what you're going to do is, now you'll say, hence, sum n going from 1, sum n going from 1 to infinity, expectation of Sn over n to the 4 is going to be less than or equal to 3k sum n going from 1 to infinity 1 over n squared, and this is going to be finite. Okay, anyway, this is going to help us reach the appropriate conclusion, but we can do that tomorrow. Any questions? Okay, so can I just have a word with Saraswati before? Saraswati, do you have a minute before your next class? I just want to talk to you about your registration.
Yes.
Okay. All right, so your advisor is Neil, right?
Yes, sir.
Okay. Have you talked to, by the way, the rest of you can go if you like. One second, let me stop recording this. We need to record this. Okay. Mukesh Verma's Google Drive. This